Hello, I'm Jacob Hughes, and this is my lab report for Physics 2212 Lab 5. The purpose of this lab was to create a model that demonstrates Faraday's law. The results were that the experimental time was 1.302 seconds, and the computational time was 1.378 seconds, and the concepts used were Faraday's law and magnetic flux. The assumptions made were that the magnet could be modeled as a dipole, the system is isolated, and there is no outside magnetic field being acted upon the system, and that air resistance is negligible. So for the experiment, we first had to find the north pole of the magnet, and then from there we drop the magnet down a tube of aluminum foil and calculate the average amount of time it spends in the tube over the course of 5 trials. To find the time spent in the tube, we take from the moment the magnet is dropped to the moment the magnet enters the tube to the moment the magnet exits the tube. So for our calculations, our values are that the tube has an outer radius of 3 centimeters, an inner radius of 1.7 centimeters, and a length of 30 centimeters. The magnet has a mass of 0.018 kilograms and a dipole moment of 2.118 ammeters squared. And the times found were, through trials 1 through 5, we have times of 1.17 seconds, 1.21 seconds, 1.67 seconds, 1.28 seconds, and 1.18 seconds respectively, which averages out to be 1.302 seconds. So here is the code. Here you can see on the left the graph initialization for our velocity versus time graph. At the bottom on the bottom left, we can see where the tube of aluminum foil is initialized, and that is continued up on the right. On the left, we are creating the bar magnet using the values that we have found and setting initial conditions for the experiment. Then we simulate dropping the magnet through the tube, which is done using this while loop on the left, which has a nested for loop on the inside. And then on the right, we have the output of the amount of time spent in the tube. And here is what the graph output looks like here. This shows that the time spent in the tube was calculated to be at 1.378 seconds. So the conclusions that can be made are that the computational model's value is very similar to the experimental value, with readings of 1.378 seconds and 1.302 seconds respectively, and that the induced current via magnetic flux creates a second magnetic field which acts opposite the first. And the what-if questions: what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? By reducing the resistivity close to 0, we are thus increasing current, because resistivity and current are inversely proportional, and this would thus cause the magnet to fall very slowly, as the induced magnetic field would increase. What if holes or slots were cut into the tube? How would this affect the ring currents in the model? As you cut more holes into the tube, you are decreasing the amount of ring currents, and the magnet would thus fall faster, as there is less of an induced magnetic field created as the magnet falls through, and thus less magnetic force acting against it.